Okay, now welcome to video class 6, and in this video also we'll be dealing with the topic modeling of physical systems part 3. Okay, now I'm going to do one more problem under this electrical systems. So under the physical systems, as I already mentioned, that there are two types which you need to study, that is the electrical system and mechanical system. So far we have been dealing with electrical system, and I'm going to do one more problem for this under this electrical system. Okay, now you can find a lot of solved problems in textbooks, in various textbooks, and you may do those things as exercise. So to find the model of any electrical system. Now, the primary thing of any just I'm going to have a recap of that. Say if you have any circuit, something like this. Say assume that you have a circuit inside this. First of all, what you need to understand is, if you want to know the find the modeling, you should identify the input as well as the output and get as many equations as possible, either by applying KVL or by applying KCL. So get as many equations as you can and substitute in such a way that finally you get a total relationship which includes only the input as well as the output, so that from that you can find out the ratio of the Laplace transform of output to Laplace transform of input. That is your transfer function. That is the meaning of modeling of a physical system. Okay, now let's move on to one more example. Example 3. Okay. Okay. Now the question is, find the transfer function of an inverting amplifier as shown. You are very much familiar with this inverting amplifier. You have studied in the op amps, linear integrated circuits. Here you have this op amp, and assume that this op amp is an ideal op amp. So its input impedance will be close to infinity, so that you know that this is a voltage source in connected to this inverting terminal. Non-inverting terminal is grounded, hence this is an inverting amplifier, right? Now it works as an amplifier because of this feedback, right? Now what happens is, this because of this voltage source you have a I1, it's moving towards this node N, but it will not enter into this op amp because of its very high impedance or infinite impedance, right? So therefore what you can say is the current through this is zero. So to find out the current I1, so you know this is the I1 which flows I1. Say let us denote this as I1 of t, and this is I2 of t, right? Time domain. So let's try to write down the time domain equation. Okay. Now what is I1 of t? I1 of t is, see what happens when current flow comes to this junction. This won't go through this, right? Because of its high impedance. We are assuming that this is an ideal op amp, hence no current flows through this. So the current flowing through R2 is 0. That means Vp is also equal to 0. So that means what the potential at this, so at this will be equal to the potential at this point, right? Okay, so that's the I mean you might have learned about that in your op amp, why these two are the same, because no current flows through this, so the same potential Vp and Vn will be of the same potential. That means when you write the equation for I1 of t, which is V1 of t minus Vn of t. What is Vn? Vn is the voltage at this n divided by R1 or R1, right? So this is also equal to, now what about this Vp? Vp is actually 0. Why? There is no current flowing through R2, so no voltage drop across R2, hence Vp is 0. Since Vp is equal to Vn, Vp of t is equal to Vn of t, you can write this as V1 of t minus Vp of t, okay, Vp of t divided by R1, while Vp of t is 0, so you can write this as V1 of t by R1. So what is the transformed equation? Transformed equation will be I1 of s is equal to V1 of s by R1, right? Now, similarly, you have also studied in your class that to find out this I2. I2 is shown in this direction. So, I2 of t is nothing but you can write this as say this output voltage as V0 of t. So, this V0 of t minus Vn divided by Vn of t divided by what? Divided by Rf, or this is equal to V0 of t minus or this is equal to V0 of t by Rf, right? Now what about this I2 of t? So when you have the transformed equation, it is I2 of s is equal to V0 of s by Rf, right? Now coming to this node, you are going to apply KCL. What about KCL? KCL states that the incoming current is equal to outgoing current. So from this circuit we can say that to this node these two current comes. So what will be the applying KCL at n? KCL at n means I1 of t plus I2 of t is equal to 0, or as per the transformed equation it will be I1 of s plus I2 of s is equal to 0, or what is I1 of s? I1 of s is V1 of s by R1, V1 of s by R1 plus V0 of s, V0 of s by RF, V0 of s by RF is equal to 0, or you can write this as, you can bring this V1 of s by R1 is equal to minus V0 of s by RF, or you can take the ratio like this, V0 of s by V1 of s is equal to minus RF by R1, right? So this is the transfer function, that is the Laplace transform of output to Laplace transfer of input. So you might have studied this in the time domain. Okay, you have derived this equation, the same equation in time domain in your LIC class. Okay, so this is the way it should be done. Okay, so this is your example 3, and I will be giving you a question based on to find the transfer function of a non-inverting amplifier that you should do by yourself. Okay, and you can expect an assignment on that through the Google Classroom. Okay, so so far we have been doing some examples of of electrical systems. That's the modeling of electrical systems. And as I've mentioned earlier when we start this topic, that we have two systems. That is, one is the electrical system and the second one is a mechanical system. In the mechanical system you can have translational system as well as a rotational system, and we will be dealing only with the mechanical translation system. Of course, in your syllabus it is given as modeling of mechanical system. So rotational system can also be asked, but for the meantime I will be only explaining the translational system. After having an understanding of this, you can study the rotational system by your own, and if because of the constraint of time, so if time permits, I'll be giving later on, I will be giving you a lecture on this mechanical rotational system, or okay. Anyway, for the meantime, we'll restrict our discussion onto this mechanical translational system. Now, we have studied that, say, in an electrical system, you have the three components, that is the resistance, capacitance, and inductance. So similarly, so by this components, an electrical system is formed, right? And we know how to find out the transfer function. By modeling, it refers to the transfer function. Now, first of all, the first step is to identify the output and the input, and get as many equations from the network by applying KCL and KVL. That are they are the available laws, and using those laws you can frame up different equations, and using proper substitution you can arrive at the equation which only consists of the input as well as the output. So once you found out that input and output, you just take the ratio by assuming the initial conditions to 0. You will be finding out the transfer function. Now once you found out the transfer function, that is the modeling of an electrical system. Now the first thing that we want to study is in a mechanical translational system, or generally in a mechanical system, you can identify three components corresponding to this R, L, and C in an electrical system. So they can be pictorially represented as this, and say this is it. So these are the three components. I'm going to name this. This one is called as the mass, and usually represented by the quantity mass is represented by M. While this is not inductance, this is actually the spring. This is the spring by which the mass may be attached to a surface. So this can also be a part of a mechanical system. So it is not necessary that all the mechanical system should possess all these three. Just as we find, say for example, if you consider an RC circuit, you will have only resistance and capacitance. So there you can't find the inductance. Okay. Now this component is called as a damper. Okay. Now the spring actually brings this mass to equilibrium when this mass is moved, while the damper actually what happens is because of the spring action, the system can oscillate, and the damper brings down that oscillation. So this the effect of the action of both the spring and the damper will make the system in an equilibrium position. Now what you need to understand is it is in this mass, on the mass a force is applied. Okay, so the capital we usually represent that as F of t. Okay, so what is F of t? F of t is the force that you act, and it is equivalent to the input voltage or input current in an electrical network. Okay, now we'll study about that later. When we study about the analogy, we are going to study about force voltage and force current analogy. That's a different topic. We'll come to that later. Anyway, so the input force that is represented as capital F of t, while the mass is represented as m, and the damper and spring, these are the name of these components, while the spring as well as damper exerts a force or this force, that is the input force which is applied on the mass, gets distributed to the spring as well as the damper. Now the spring, coming to this damper, this is having a coefficient called as a damping coefficient, which is represented by small letter f. F is a constant damping coefficient. So this f is called as the damping coefficient. Okay, this is damping coefficient, and so this is actually, now in the case of spring you have another constant which is represented by k, which is called as a spring constant. Okay, so the mass is represented by m, capital M, which is the mass. The spring represented by its constant called as a spring constant k, and damper, which is represented by its coefficient called as a damping coefficient f. So all these are constants. Now let us see, when a force F of t is applied to this force gets distributed throughout these components. Now the force due to a mass, let's call this, for the meantime let us call this as Fm, F capital M. It is proportional to what? Proportional to d square x by dt square. This you know from your +2 physics. So this is actually equal to m into d square x by dt square, or this is the basic expression, mass into acceleration. So if there is a mass, the force exerted on the mass will be depending on the acceleration of due to, I mean, when a force is applied to the mass, definitely that mass gets displaced. Now if there is a displacement, there can be a velocity. If there is a velocity, there can be a acceleration. And if the acceleration is experienced by this mass, and that acceleration multiplied by m will give you the force acting on that mass, or the force contributed to that, distributed to that particular mass. And similarly, um, the force due to spring is proportional to, say, let us call that as Fs. Fs is proportional to, okay, I will come to damper first. Say the force due to the damper is proportional to dx by dt. It is not proportional to the acceleration. This is proportional to the velocity. So this is f into dx. This is equal to f into dx by dt. Now what about the spring? Now when you coming to the spring is proportional to the displacement, or it is equal to kx. Okay, so this is how the force equations corresponding to each components, and these force equations are generally called as or generally derived from D'Alembert principle. So questions are usually asked for 2 marks question, as 2 marks questions as what is D'Alembert's principle. So it is actually the force associated with the mass, spring and the damper, and how it is related, that is being given by this D'Alembert's principle. Now we need this D'Alembert's principle to frame up the equation for a mechanical translation system. As I told you, in an RLC circuit, if you want to find out the transfer function, the first requirement is to get as many equations as possible by applying the suitable electrical laws. So similarly, by applying D'Alembert's principle as well as Newton's laws of motion, you can derive, or you can come to various set of equations. Now using those equations properly, you can find out the Laplace transform of output to Laplace transform of input, and which is going to be the transfer function. Once you found out, that's it. So that is called as the mathematical model of such a mechanical system. Okay, so here is an example of a spring mass damper system. This is equivalent to a simple RLC circuit as we see in electrical system. It consists of a mass and a spring and a damper. Now you should understand where the force is applied. The force is always applied to on the mass, right? Now when a force, so here the force is given as f of t, and that will result in the displacement of the mass. Okay, now when it displaces, what the spring and the damping coefficient say does is, the spring will be having a restoring force. That means the spring always tries to bring back to its equilibrium. That's called as a restoring force. The force we call produced by this spring is called as a restoring force, and that is given by this expression Fs is equal to kx, right? So it's proportional to the displacement. Now what the damper force does is, it always offers a viscous force or a frictional force, viscous force. Okay, and that is being given by this expression, that is equal to this expression F into the derivative of the displacement. So look at this. So when a mass is moved, these two will work in such a way that one will try to maintain its equilibrium, the other one will oppose its action. So that's the work, or that's the task of these two damping force. Now in this system, what we are going to, just as we apply KVL or KCL in a series RLC circuit or a parallel RLC circuit, what we do here is, since it's a motion, we can apply Newton's second law of motion, right? Now relying on Newton's second law of motion, we can write that what is actually Newton's second law of motion. You can say that the inertia is actually equal to the force acting on the body, okay? So it is, so the force inertia, the inertial force is actually equal to the force acting on the body. So the net force actually makes the mass to move. Now let us see, let us fill this equation. Now what is this inertial force? That is the inertial force due to the mass. We know that that force is given by m into d square x by dt square. So this is m into d square x by dt square is equal to what is the first force that is acting on it? You can say that this is, say, and this is given as f of t. Okay, so that is the first force acting on it. Now when this force is acting on the mass, definitely the mass moves, and the spring and the damper will act against that, right? Again, so the net force will be in opposition to the force acting on the mass. So the force on the inertial force, so it always opposes the motion. And so you can write this as, since it is opposition to this f of t, so this is a total force that you apply, f of t. And since these forces are opposing, we put a negative sign. So this will be what? What is the force due to damper? The equation is f into dx by dt. So this is f into dx by dt. Then what is the spring? What about the spring? The spring is actually minus k into x, right? Okay, mind you that this x is actually a function of time, that is displacement, so it is x of t. So for the meantime, I'm just writing it as x, so this is kx. So this is how it goes. Now this one is the input, and what is your output here? The output is the displacement. So this one is the input, this one is the output. Now what you need to find out is, you want to know the transfer function. So if you think that this f of t and x of t, say call this is x of t, x of t is the output, what will be the transfer function of this? The transfer function will be, as per our definition, it will be the Laplace transform of f of t. Let us call that as f of s, right? Sorry. So the transfer function is equal to the Laplace transform of the output, which is sa x of s, divided by the Laplace transform of the input, which is f of s. So if you can find out that from this equation, you will arrive at this transfer function. Let's have a trial. Say what is next. So this is actually a differential equation, right? So this equation can be rewritten as m d square x by dt square plus, bringing all these to, f into dx by dt plus kx is actually equal to f of t. So you can, you can also do, see one more thing, a principle of conservation of energy. That is, you're applying energy in the form of force, and it gets distributed along the mass, along the damper, or dashpot damper it is usually called. This is usually called as you may note it, dashpot damper. Okay, now damper, and it is also been contributed by the spring. Okay, now this is it. So now what's next? Applying the Laplace transform throughout this equation, you will be getting m into s square into x of s, and you have a tail like minus and minus something and something, and those will be neglected. Why? The reason is the transfer function is defined for the initial condition to 0. So this is m into s square x of s plus f into s into x of s plus k into x of s plus is equal to, what about this, f of t, that is f of s. Okay, now what I need to know is x of s by f of s. You can take this x of s outside. So taking x of s outside, you will get this as ms square plus fs plus k, right? K is equal to f of s, and you want x of s by f of s. So this is, when you bring this f of s to the denominator, you will get this as 1 by ms square plus fs plus k. And what is this? This is actually the transfer function of this simple mass spring damper system. Okay. Now, next is we are going to talk something about the analogy with the electrical systems. With the electrical system. Okay. So, we know that in an electrical system, the input energy can be either in the form of V of t, which is the voltage, or current. While in a mechanical system, it is actually F of t, that is the applied force. So you can say in a sense that this applied force, it can be equivalent to either voltage or current in an electrical system. That means you can have two types of analogy with the electrical system. That is the force to voltage analogy system and the force to voltage analogy and the force to current analogy. Okay, right? So this is also analogy, right? Okay, now to find the force voltage analogy, we are going to consider, so in order to find out the force voltage analogy, you should consider a series RLC circuit. Okay, so consider any series RLC circuit, say with some E of t is applied to RL and C. Okay, so this equation, so this will be generating a current, say I of t. Now you can write the voltage equation by applying KVL. So applying KVL, you will get E of t is equal to, what about the R into I of t, R into I of t plus L into di of t by dt plus 1 by C integral I of t dt. Okay, so this is the first equation. Now we know that this I of t actually can be considered as, this I of t is nothing but it is the rate of flow of charge, right? Current is defined as the rate of flow of charge. So you can equate where Q is called as a charge, and if you know the rate of change of charge, that results, or when charge moves, that results in current. So there must be some rate, and it is the rate of the flow of charge is defined by a parameter called as a current. Now you can substitute this in equation 1. So substituting in 1, you will get this as R into dq by dt, right, plus L into d by dt of what, dq by dt, right, plus 1 by C integral d by dt dq by dt, right? Now what is this? This is actually this is R into dq by dt. What about this? This is L into d square q by dt square plus, what about this? Integral of the derivative of a function is that function itself. So this charge is a function, so this will be q by C, right? Now rearranging this, we will get this as L into d square by q by dt square plus R into dq by dt plus q by C actually equal to E of t. Okay. Now what is the next step? In order to, now our objective is to find out an analogy between the force and voltage. Now we have the voltage equation right now. Now I'm rewriting the force, the only force voltage equation which we have already derived. Say this expression, m into d square x by dt. So I'm rewriting that as m into d square x by dt square plus plus f into dx by dt plus k into x. Okay, so this is called, this as equation 2 and equation 3. This is equation 3. So now what is the meaning of analogy? Because all the things, that is the applied force or be the components, all has got a corresponding component in the mechanical side. So you are actually going to relate each and every mechanical components to an electrical system. So the advantage of that is any mechanical system can be converted. If you know the corresponding electrical components of that, you can have an electric circuit corresponding to any mechanical system. And once if you know that, it's very easy to analyze a mathematical sorry a electrical system using these tools. So that's why we are correlating this electrical system to mechanical system. Now in comparison to this sounds similar, no? 2 and 3 are similar, right? So you have some function is equated to something into d square plus something into dq dx plus something into a constant or q by c. Now let's see. So this is let us see the analogy of this. Now you are going to find out this say let's have a this thing. So let's have this mechanical system corresponding electrical component. Now in the mechanical system we say force, that is the applied force, right? In the mechanical system you have the applied force, and applied force is equal to, this is electrical, what type of analogy? This is force voltage analogy. So I told you there are two types of analogy, and we are dealing with the first one, that is a force voltage analogy. So when you have the applied force, that's the equivalent of that in the electrical system is the applied voltage, right? So this is the applied voltage, right? Now next let's go to the equation. So there is a d square q by dt square and d square x by dt square. Okay, let's have this q and x. That is, in the mechanical system you have the displacement. Due to the force you have displacement, while in an electrical system the corresponding thing is what? It is equal to the charge. Okay, now let's move on to this L and mass. In the mechanical system you have mass, which is equivalent to inductance in force voltage analogy. Okay, inductance. So charge q, this is L, this is say E, this one is f of t, displacement, this is x, this one is mass. Now next one is you have resistance and F. So the frictional force or the viscous force, the frictional or the damping force, or it is called as a damping force, is equivalent to what? Is equivalent to, damping force is equivalent to the resistance in what, in this thing. Now coming to the dx by dt, then you have q by c. Q is equivalent to x, right? So q is that we have already found, that is the displacement is equivalent to charge. Now finally, what about the spring constant? The spring constant is equivalent to k into x is equal to q by c, or is equivalent to q by c, meaning the spring constant is equal to, that is the frictional okay, this is damping constant. I think that will be nice, damping constant or the damping coefficient. Here you have the spring constant, which is equivalent to what? That is k, this one is f. K is equivalent to what? 1 by c, or the reciprocal of the capacitance. Okay, so hope you understood this analogy. So that's it. That means in a force voltage analogy, the applied force is equivalent to the applied voltage. The displacement resulted will be equivalent to the charge flow, and the mass is equivalent to inductance. Now the frictional coefficient or the damping force is equivalent to the resistance offered by the electrical circuit, and the spring constant, okay, the spring constant is equal to the reciprocal of the capacitance. Okay, now the second one is the force current analogy. Now in this that's the second one. So here we are considering the applied energy to an RLC circuit as current. So for this we consider, instead of series RLC circuit, we consider a parallel RLC circuit like this. Okay, now considering this parallel RLC circuit where we give the input as the input current, right? So call this as I of t, this is R, this is L and C. Okay, Now applying KCL to this equation, that's what we are going to do. Now when you apply this, first of all you should assume that the parallel branch, there is a parallel branch, R, L and C are parallel. So there is a voltage. Assume that you have a voltage across this branch, and this, let it be E of t or E. So this is the voltage developed across the parallel combination. Okay, and that is a voltage developed across the resistance, same as the voltage developed across the inductance, and same as the voltage developed across the capacitance. Okay, now before going to apply this KCL, what is actually KCL? KCL is actually current, Kirchhoff's current law, that is the incoming current is equal to the outgoing current. Now it is customary to see that the incoming current will be always taken as the direct current that comes from the current source. So you have a current source I of t, so I of t coming to this node, meaning this is the incoming current to this node, and all other currents leaves from this node. Now what will be, let's see what is the current through R, L and C. So you have IR, it is equal to E by R, that's from Ohm's law, no? E, this is the voltage developed across resistance, so it is equal to E by R. And if you have the voltage developed across the inductance, then you can find out IL by using this equation, 1 by L integral E dt. Now from where did you get that? That is, you already know VL is equal to L into di by dt, and from this, if you can integrate this, you will get integral VL dt, bringing this L down, that then becomes, when you integrate this, you will get I of t. So from that you got the current equation, the inductor current equation, and capacitor current is given by C into the derivative of the E of d of by dt. Now we have just assumed that the the voltage developed across this parallel combination is E, and that will be the same for inductance as well as capacitance. Now we are just relying on a characteristics of inductance. We know what is this inductance. Okay, characteristics of inductance, that is the back EMF. So the inductance, in the inductance, the EMF is proportional to, or it is equal to, the rate of change of flux, right? Okay, the rate of change of flux, and that is given by psi. So E is equal to d psi by dt, right? Now after knowing this, we are going to apply KCL. Now what is KCL? The incoming current I of t is equal to IR plus IL plus IC. Okay, now you have we have seen that this is, now combining these together, E by R plus 1 by L integral E dt plus C into dE by dt. Now what is this E? E is actually the flux linkage, or, and we are assuming the flux linkage, the symbol is psi. So the rate of change of flux is actually EMF, or it is called as the back EMF induced by this inductance. So that back EMF has to be the drop, has to be the voltage across. This voltage has to be the same as this back EMF. So this is equal to d psi by dt. So you can make use of the characteristic of inductance here. So then substituting in this equation. Okay, that's what we do. Substituting that in this equation, you will get this I of t is equal to 1 by R into d psi by dt plus 1 by L into integral d psi by dt plus C into d by dt into d psi by dt, right? Now now you can have this as 1 by R into d psi by dt plus 1 by L into psi integral of the derivative of that function is that function itself plus C into d square psi by dt square. Now you can rearrange and like this, C into d square psi by dt square plus 1 by R into d psi by dt plus 1 by psi into by L, right? Now this is I of t. This is actually I of t. Now again you are going to compare with the equation f of t is equal to m into d square x by dt square. This is a mechanical equation plus f into dx by dt plus k into x. Okay, now also you are going to have a table. Here you have a mechanical uh, uh, mechanical parameters, while this here you have an electrical parameters. Now when you compare with this, the applied force is equivalent to what? Equivalent to the main current. Okay, or the injected current. We will call this as an injected current or the main current. Okay, so this is your I of t. Now what about displacement? Displacement in a mechanical system is equivalent to what? The flux linkage side, right? Okay, so this is actually the electrical system. What type of analogy? Force to current analogy. Then what about mass? Now mass is equivalent to capacitance in current to voltage analogy. You can have a comparison to voltage analogy. We found the mass to be equivalent to inductance in force to voltage, while in force to current the mass is equivalent to capacitance. Now what about the damping force or force damping coefficient? Damping force or damping coefficient is equivalent to what? Equivalent to the 1 by the reciprocal of resistance 1 by r, or you will call this as the conductance. This is C. Okay, that is the damping force. Now what about the spring constant? Now the spring constant is equal to the reciprocal of inductance. Okay, 1 by L. Now you can have just a comparison of these two analogy. In force voltage analogy is totally different from force current analogy. So hope you understood